the boys. All the boys want to share.
Okay, 5-4. I do not know if this is going to end up being a day 1 and day 2, so we'll play it by ear. We are going right into an example to get a little theorem discovery going on here. I know. We're going to have a population of values. What does population mean?
That means everybody.
That's everybody. We have a population that has 4 people in it.
Oh.
2,
Is this in Wyoming?
4, 6, and 8. That's it. Okay. We are going to take samples of size 2. This is the basis for statistics. Like all this political stuff that's going on, you'll do that polling business. They do a small sample from a population to determine what the entire population is doing. You know how like on the presidential election they'll call with like 3% of the vote in who's going to win? And people will concede? And it's all statistics based. So if their sample is good enough, you know, like they've gotten a good representation, they don't need to count all the votes. I mean, they eventually do, but they don't need to count everything to determine what's going to happen. So based on the trend of the small sample, you can say what everything is, what the outcome is going to be. In this, sometimes it's wrong. It depends on, and that just means their sample wasn't all-inclusive of all the different little subgroups. But this is a little basic introduction to how it all works. So if we had a real small sample with 4 things, then we're going to take samples of size 2. But before we do that, I would like to know the mean and standard deviation of my population. So put those in a list and run your 1-var stats and tell me what the mean and standard deviation are. I'll do it too. Well, yeah, what's the mean? 5. Coming from Mr. 28 on the ACT.
Wait, you got 28 on your ACT?
Yep.
Otherwise. I was trying to help you. 1-var stat. Yeah.
Stat.
I forgot how to get to that. If you have to edit things, right? Like
Yep, you got to put them in a list first. And then, which standard deviation do we want? Remember the 1-var stats gives you 2 of them. The O one, the sigma one.
Okay, 1-var stat. I found it.
Do you want a cookie?
All right, now we're going to make a big table. We're only going to do this once to see the relationship. And it's kind of a long table, so I'm going to make it the sample and then the mean of the sample. And like I said, it's going to be a long table, so instead of making one long one, I'm going to make 2 shorter ones.
I didn't get that answer.
Then you didn't type in 2, 4, 6, and 8 correctly.
That's hard.
We'll go back to stat edit. Look at your list. 2, 4, 6, 8.
Yep.
1-var stats, list 1.
What about frequency list? What do you put there?
1.
Why? I cleared it out and put nothing.
Okay. So what we're going to do here is look at every single possible sample of size 2 we can create from this population and write them all down and give the mean of that sample. And with our, when we take our sample, like pretend they're ping pong balls, you got 4 ping pong balls. I'm going to pull a ping pong ball, look at the number, stick it back in, grab another one. Okay? So I'm doing samples of size 2. And let's do this in a nice organized way because I want to list every single possible sample I could get. So I'm going to start with the 2. If I reach in, I pull out a 2. I throw that ping pong ball back in. What else could I reach in and get?
A 2.
A 2 would be best. What's the average of a 2 and a 2? 2. Okay. Let's say I reach in, I grab a 2. What else could have been my second pick?
4.
What's the average of 2 and 4? Katie, stop talking.
So you're putting the balls back.
Yes, I'm putting the balls back in. What's the average of 2 and 4?
3.
And we keep going. I could have picked a 2, and then what could have been my second pick? 6. The average being 4. And then 2 with 8. Average being?
5.
Okay. So those are all possible samples where I would have picked the 2 out first. What else could have been the first ping pong ball I took out?
3.
I don't have a 3 in there. A 4? And what with the 4? 2. What's that average?
2. No, 3.
3. 4 with
4.
4. Average being 4. 4 with 6. Average being
5.
and 4 with,
Why are you doing 4s?
because it's a possible sample for me. I could have gotten that. I'm writing down every single possible sample I could get in a nice organized way.
Wait, how do you know?
How do I know I could get those 2?
No, but I'm just confused because you said that you only wanted size number 2, so why are you...
2 ping pong balls. Size 2. 2 ping pong balls.
So is the next one just the 6?
Yep, 6 first. Then what can I get with the 6? That's a nice organized way to do it, is to go consecutively. 6 with 2. 6 with 4. 6 with 6. And 6 with 8. Let's go back and do the averages now.
Okay, I know exactly what I'm doing. 'Cause
Okay.
I did it all.
Yep.
But take samples of
Size
size
2. 2 numbers from the population.
Oh,
2 numbers from the population.
Okay, I'm gonna write the numbers.
Okay. And then what's my last set of samples I could possibly get? 8, 2, 8, 4, 8, 6, and 8, 8. So we'll have a 5, 6, 7, and 8. Okay. What I want you to do now is put all of these averages in, well, let's make a table of averages. Let's go with the mean and the frequency. So out of my averages, I got 2s, 3s, 4s, 5s, 6s, 7s, and 8s. How many times did I get an average of 2? 1 time. How many 3s came up?
2.
2 of them. How many 4s?
3.
3 of them. How many 5s?
4.
4. How many 6s? 3. How many 7s? 2. And 1. So what I want now is the average of all of these averages and the standard deviation of these averages. And we want to compare back to our original population. So we are finding the mean of all the sample means and the standard deviation of all the sample means. Okay, do you remember how to do it with 2 lists? Okay, so you got to come back, do 2 lists. So clear out list 1 and list 2. And we got 2. Now this time you will have a frequency list, Kenley, because we're going to put it in.
Okay.
So we'll run 1 var stats.
I don't have a list 2.
Do you have a list 3?
Yeah.
Then use that one. And I'll show you how to get your list 2 back later. So the average came out 5. And my standard deviation, because it's all possible samples, it's a population of samples. So I do want the sigma standard deviation here. 1.581. Okay. The whole goal here was to, the little theorem discovery kind of thing. One part of the theorem is easy to discover. Obviously, what am I looking at the easy part? The means are the same. There is a connection between these standard deviations. It's just not very obvious what it is. I could give you probably 100 years to figure it out and you wouldn't come up with it.
And how did the people?
I have no idea, but the way these two things are related is if you take this standard deviation, 2.36, or 2.236, let me write it down right, and you divide by the square root of your sample size. How big were my samples?
Was it 8?
Nope. How big was each sample? How many numbers did I have each time I picked? 2. Do 2.236 divide by square root of 2.
Got it.
Oh. Do you think you ever would have come up with that in 100 years?
I mean, maybe 100 years.
Maybe in 100 years you would have come up with that?
Yeah.
Okay. I don't know. Betsy, 100 years you going to come up with that one? Yeah. Okay, Betsy's got it.
30 minutes.
Okay.
I have better things to do.
30 minutes?
All right, so what we just discovered, we're going to write down. So there are 2 properties of sampling distribution. So properties of sampling distributions. Of sample means. Because we took the mean of the sample every single time. I'll say it in words and then I'll say it in symbols. The first one was that the 2 means were equal. So the mean of the population came out equal to the mean of the sampling distribution. So that's population mean equals the population mean of the sample means. It's the mean of the means. You're doing it twice. I know. And then the second property was that the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of the sample size. So in symbols, the standard deviation of the sampling distribution is saying the standard deviation of the sample means is equal to the population standard deviation divided by the square root of the sample size, where n is the size of the sample you're taking.
I'm not, you liar.
Liar. Liar. Yeah.
No, you could come up with it.
Yeah.
Like the rest of the class.
All right, so this next example, 2, I want you to, 4? Find
I'll be pushing it.
the mean and standard deviation of the sampling distribution if samples of size 5 are taken from population. Well, yeah, because it's once you write it out, there's no work to do other than type in the calculator. And we're going 0 through 9.
The librarian today told me she wanted to go home, so that doesn't tell you something.
Why did she want to go home?
I said I want to go home, and she
Oh.
said, me too.
Oh.
Yeah, she said, me too.
Can we all?
Are we ready?
Yeah.
Okay, so what we're looking for is the mean of the sample means and the standard deviation of the sample means. Well, we just have found the two properties. Both of these values are directly related to the mean and standard deviation here. The means are equal, and this is a little division to get the standard deviation. So what you want to do is run one var stats on this list to get the mean and standard deviation of your population. Once you know those two things, it's very simple to write down the two things I'm looking for. So it's all calculator work. You just got to type everything in correctly, Kenley.
Isn't it the same thing?
The mean is going to be the same thing. Standard deviation is not quite the same thing. So, it's one list. Zero through 9. Run your one var stats.
Wait, just one more?
One list, yep. So, the mean of the numbers 0 through 9, 4.5. Now make sure you take the right standard deviation. Which one should we be taking? The bottom one, the 2.87.
When do we take the S? Is that when it's a sample?
When it's a sample. But this was a population. You didn't type in the numbers correctly, Kenley. Check it out. She did not type in 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. She got a mistake somewhere along the line. Oh, I will bet $10,000 you don't have those numbers written in.
Sure, so we can just talk about it after class.
$10,000.
Over 10,000. Did she do one var stats on that particular list?
Okay, I got it right. Where do you go? Here. When you go to the that,
Okay, so what's going to be the mean? If I was to do samples of size 5 out of this thing and keep doing samples of size 5 and averaging those 5 numbers, what would be my mean of all my sample means?
4.5.
4.5. There's no difference. They're identical. Now the standard deviation is not the same as this one. How do I calculate it?
2.87.
Divide by
Square root of 5.
5. I was going to take samples of size 5.
Oh, there it is.
There it is. So the standard deviations are not the same, but they're directly related over here. So, oops. 1.28. All right, very good. No, it's that yet. Okay. Central limit theorem. This is the whole big idea.
Take up the last page.
Yep, I've got it on a full page. Central limit theorem.
And that's the last thing, right?
That's my central limit theorem. It all ties together.
So that's the last page of this bill.
And then we finish up with 2 little examples on the back.
You're killing me.
That's the plan today.
Do a little example?
Killer Monday.
Not gonna get all that done.
Killer Monday.
I'm gonna start straight.
Yeah, that's not
I'm
gonna happen
coming
today.
off the holiday.
Okay, the central limit theorem.
Doesn't get safety glasses on because I'm gonna turn it.
Okay, the central limit theorem describes the relationship
What do you spell theorem?
So,
What do you actually spell theorem?
Theor.
between a sampling distribution and the population. There, I shortened that up as much as I could. Okay, I don't think I'm going to bother with the 2 wordy ones because I think I can get it with the pictures instead. That might make you happier. So, the first thing. Okay,
We're all bless you, Lexi.
here's my population distribution.
Oh, that's.
Okay, ugly. My point was it's not normally distributed, but this is my population. Anything that doesn't look normal.
So we're just gonna draw anything we want to.
Yep, just don't make it look like that nice little bell-shaped symmetrical curve.
Mine looks like coral.
Okay, I think mine does too.
It looks like coral.
So your population is not normally distributed. It's some ugly distribution, looks like coral. But you will be able to find the mean and the standard deviation of it. We'll just throw the mean here. And it has some standard deviation. Now, if you take samples that are at least 30 in size, so take,
Let's straighten it out.
it will, samples, size n, but you have to be at least 30 in size or bigger.
What are we even talking about?
Or talk about maybe
right now.
prettier.
Okay? Your sampling distribution will come out normal. So you're going to take something very, very ugly and turn it into a nice normal distribution where we can do lots of statistics with it. And what do you think is going to be the relationship between the mean of the population and the mean over here?
They're gonna be the
they're going to be the same. So the mean here will equal the mean of the population.
Can we just leave it ugly?
And what do you think the standard deviation here will be? Not the same. What was it that we just discovered?
If you divide.
All those shenanigans.
It was this standard deviation, the population's divided by
30.
the square root of whatever. It doesn't have to be 30, it's got to be 30 or more, so whatever size you take. I could take samples of 100 if I want. Okay. All right, there's a second situation though. Maybe you do know your population is normally distributed to start with. So this is the second case. If my population is normal, population is normal, it will have a mean and standard deviation. This time when I take samples, you won't have to hit that magic number of 30. You can be under 30 and your sample distribution will still be normal. So now I can take any sample size. And I will still get a normal distribution. I kind of want to put it on top of that one,
I kind of don't want it.
because I want to show that what happens, because I'm dividing by the square root of the sample size, it's just going to shrink, it's going to make it a narrower graph. That's why I kind of want to put it back on here. I'm going to go back this way. And I'm going to grab another color.
Why don't you just...
So this is the population out here. The sample distribution, I'm going to go in red,
Wait, are you gonna make another one?
right inside, because what's going to happen is it's going to get a lot narrower but have the exact same mean.
It's kind of ruining the whole thing.
I know, but it's the best way to tell what's happening. So there's the sample one.
So there's nothing going to the right of that?
No, we're not going to put anything over there. Well, I couldn't show that it was narrower over there. But the sample, the mean here, again, will equal the population mean. And the standard deviation on the sampling distribution will be that population one divided by the square root of the sample size.
Did you mean to say population?
I may have, I don't know. The standard deviation of the sampling distribution will equal the population standard deviation divided by the square root of the sample size. I don't know what I said, but I said it right that time. Okay, so both sampling distributions, the means and the standard deviations relate directly back to the population. The trick is, if you don't know your population is normally distributed, you have to take at least 30 samples, and then you're good to go. The more samples you take, the more chance of being correct in your predictions. So the last two little examples.
Are they like
The half page
one-liners?
sufficient for this?
Are they like one-liners and all?
No, they're not one-liners. I wonder if I want to do this tomorrow.
Yeah,
Do it tomorrow.
Yes, please.
I think I will. Or, well, let's do one. I'm just going to do one quick example, then I'm going to save that for tomorrow. One example.
Hold on, short.
What?
Show me the bottom of that again.
Show you the bottom of that.
Get this sample.
Yep, I just wrote out what the mean and standard deviation are coming out. Okay, one example.
So, wait, quick question on that.
Yes.
So for the sample, because I do like what was originally, it'll be narrower?
Yes.
Oh, okay.
Okay, there we go. Our one example. Number 3. Okay. The diameters of oak trees are normally distributed. With a mean of 3.5 feet and standard deviation of 0.2 feet. I want you to sketch the population and sample distributions if you are going to take samples of size 16. Size 16. So what you would be doing is randomly selecting 16 oak trees, finding the diameters, averaging that together. Take another sample of 16, find the diameters, average them together. What will those two distributions look like? And I want to know the mean and standard deviation of the sampling distribution. Find the mean and standard deviation of the sampling distribution. All right. So we're going to sketch two graphs on one axis, just like I did on that last little introduction there. So what do I know about the diameters of my oak trees? What did I tell you? Normally distributed. That means they're that nice smooth little bell curve. Where the average is 3.5. Standard deviation is 0.2, so that would be 3.7. Not that we need all of these, but that's good enough. Okay? Because my population is normally distributed, did I have to take the magic number of 30 to get a normally distributed sample?
No.
No. So what shape is my sampling distribution going to have? Normal, just going to be skinnier because it's going to have that smaller standard deviation. So there's my sample. And then I want those two values. The mean of the sampling distribution and the standard deviation of the sampling distribution. The mean is 3.5, nothing tricky there. It's the same as the population. How do I figure out what the standard deviation is that's making it smaller? 0.2 is the standard deviation. Don't take that value, take the standard deviation, which was 0.2.
Divided by the square root of
divided by the square root of 16. So what does that come out? Was it? 0.5. Okay. You made it. Now I gotta find a homework assignment.
Or we could just find that, not do it.
Oh, you could. That. This was a day one. If you want to go back and put day one at the top of that.
What are we going to be doing tomorrow next?
What's that?
How much are we going to be doing?
Probably not as much as this. Just some examples, I think. Let's see. 5. 4. Let's go page 230. Okay, when it says list all samples with replacement, we're never ever, that was that big list we made, don't do that. Just find the mean and standard deviation like it says. So anytime it says list, don't do that. We're going to go 1 through 4. Central limit theorem to find the mean and standard error of, oh, I forgot that. Oh, shoot. Hold on. That just went one definition there. This,
What We'll do it tomorrow.
Yep, it's just a word that they use. I didn't use it. I kept calling it standard deviation. This standard deviation of the sample, it is standard deviation, but they refer to it as the standard error.
Standard what?
Error. Standard error. It just means, when you see standard error, it means it's the standard deviation of the sampling distribution. So I keep saying that, standard deviation of the sampling distribution. They just give it a new name, standard error.
That's stupid.
So you don't have to keep saying standard deviation of the sampling distribution.
Go.
My 6 words get limited down to 2. Okay, so when you see that, glad I read that, we're going, let's go, not too many here. Let's go 5 through 9 odd. And then we're going to pick up 11 and 12. This is not much. Okay. Yes, let me turn this off.